There is a number so fundamental to the structure of reality that the universe itself seems to have been engineered around it. Not as a guideline, not as a suggestion, as an absolute ceiling, a hard wall woven into the fabric of space, time, and everything that has ever existed or ever will. That number is 299,792,458 meters per second. Nearly 300,000 kilometers every single second. The speed of light. Every photon that has ever left a star, crossed a galaxy, or landed on a human retina has traveled at exactly that speed. Not approximately. Exactly. In a vacuum, light does not accelerate, does not decelerate, and does not deviate from that figure by a single meter per second. It is not a record waiting to be broken. It is the definition of the fastest anything in this universe can move, and the reason why is not a matter of engineering. It is a matter of physics so deep it reaches into the geometry of space-time itself. We are, as a civilization, barely adolescent in cosmic terms. We have been launching objects into space for less than 70 years. The most distant human-made object ever built, Voyager 1, was launched in 1977 and has been traveling through the void continuously for nearly 5 decades. It moves at roughly 17 kilometers per second, an extraordinary achievement by any human standard. And yet, to reach the nearest star beyond our sun, Proxima Centauri, at that speed, Voyager 1 would need approximately 73,000 years. Not decades, not centuries. 73,000 years of uninterrupted travel through cold, empty interstellar space. For context, 73,000 years ago, modern Homo sapiens had not yet migrated out of Africa. The Sahara Desert did not exist. The world was locked in the depths of an ice age. That is the scale of the problem. Not a political problem, not a technological problem, at least not primarily, a physical one. The dream of traveling at the speed of light, or even a meaningful fraction of it, has been a fixture of human imagination since the moment we first understood that stars were not holes in a dome but distant suns, many of them unimaginably far away. Science fiction built entire civilizations on the assumption that we would eventually find a workaround. Warp drives, hyperspace, fold drives, wormholes traversed in an afternoon. These concepts have become so embedded in popular culture that billions of people carry a quiet assumption that interstellar travel is simply a matter of time and political will. That given enough centuries, enough resources, and enough engineering ambition, humanity will one day point a ship at another star and arrive in a reasonable human lifetime. That assumption rests on a misunderstanding so fundamental and so rarely corrected that it is worth addressing with full scientific weight before anything else. The speed of light is not fast because of how fast it is. It is a limit because of what it is. Light, or more precisely, electromagnetic radiation, does not travel fast by coincidence. It travels at that speed because it has no mass. A photon, the particle that carries light, has zero rest mass. That is not a poetic way of saying it is very light. It means a photon, at rest, does not exist. It cannot be at rest. The instant a photon is created, it is already moving at the maximum possible speed allowed by the universe. It has no alternative. Now ask the inverse question. What happens to an object that does have mass, any mass at all, as it accelerates toward that limit? This is where Einstein's special theory of relativity, published in 1905, enters the picture with the full weight of over a century of experimental confirmation behind it. The relationship Einstein described between mass, velocity, and energy is encoded in the most famous equation in the history of science, E equals mc squared. But that equation, as it is usually taught in school, describes rest energy, the energy locked inside a stationary mass. The fuller picture, the relativistic version, describes what happens to a moving object. And what it describes is this. As an object with mass accelerates toward the speed of light, its relativistic mass, the effective resistance it offers to further acceleration, does not stay constant. It increases. The faster the object moves, the heavier it effectively becomes. And the heavier it becomes, the more energy is required to accelerate it further. This is not a mechanical problem. You cannot solve it with a bigger engine. The mathematics are exact and merciless. As an object approaches the speed of light, the energy required to accelerate it further approaches infinity. Not a very large number, infinity. To actually reach the speed of light, an object with any mass at all would require an infinite amount of energy. And since the total energy available in the observable universe is finite, enormous but finite, the speed of light is not a barrier that can be broken with sufficient thrust. It is a mathematical wall embedded in the laws governing space and time. Think of it this way. Imagine you are pushing a cart. At low speeds, each push accelerates the cart by a predictable amount. But now imagine that every meter per second you add to the cart's speed, the cart also gains weight. A little at first, then more, then much more. As you approach some final speed, the cart has become so heavy that a push capable of leveling a city block adds almost nothing to its velocity. Eventually, no push, no matter how powerful, could make it go any faster. That is the experience, translated into human terms, of relativistic mass increase. Except in reality, the numbers do not just grow large, they grow without bound. The barrier is not in the rockets. It is in the nature of mass and energy and the structure of space-time. This principle has been tested, confirmed, and relied upon by physicists and engineers for over a century. It is not theoretical in the speculative sense. It is theoretical in the same sense that the theory of gravity is theoretical. Particle accelerators around the world, including the Large Hadron Collider at CERN beneath the border of France and Switzerland, routinely accelerate protons to speeds exceeding 99.999% of the speed of light. The energy required to push those protons that last fraction of a percent faster is extraordinary. The entire facility consumes roughly 1.3 terawatt-hours of electricity per year, comparable to the power consumption of a mid-sized European city. And those protons are among the smallest, lightest particles of ordinary matter that exist. A spacecraft, even a stripped-down hypothetical probe carrying no crew, no instruments, nothing but its own structural mass, would require energies that dwarf anything the current or foreseeable human civilization could generate. By factors that are not merely large, they are incomprehensible. There is a further layer to this that is almost never discussed outside of physics classrooms. Even if the energy problem were somehow, magically, impossibly solved, the traveler would face a different consequence. Time itself would change. At velocities close to the speed of light, time on the moving spacecraft slows relative to time on Earth. At 99% of light speed, time aboard the ship passes at roughly 1/7 the rate of time back home. At 99.99% of light speed, the ratio becomes extreme. A journey that felt like a few years to the crew could correspond to centuries passing on Earth. The ship returns. Everyone who saw it leave is dead. Their grandchildren's grandchildren are old. The universe does not make speed free. The closer you push toward the absolute limit, the more you pay, in energy, in mass, in time itself. And that is only the beginning of the problem. The speed of light is not a challenge to be overcome. It is a property of the universe as fundamental as the number of spatial dimensions we inhabit. Understanding why, truly understanding why, at the level of geometry and physics rather than science fiction, changes everything about how we think of humanity's future among the stars. The answer requires going much deeper, into the structure of space-time, into the physics that makes the vacuum of space not empty, but seething with energy, into the history of the scientists who tried, over more than a century, to find the edges of this wall, and what they found instead. The 19th century ended with a crisis that most people outside of physics have never heard of. It was not a crisis of politics or economics. It was a crisis of measurement. And it cracked open one of the most confident assumptions in the history of science, that space itself was filled with an invisible, motionless medium through which light traveled, the way sound travels through air. Scientists called it the luminiferous ether. And for nearly 300 years, almost everyone believed it existed. The logic seemed airtight. Waves need a medium. Ocean waves travel through water. Sound waves travel through air. Seismic waves travel through rock. Light, which behaved unmistakably like a wave, It diffracted, it interfered, it polarized, had to be traveling through something. The universe could not be full of nothing. So the ether was not a fringe hypothesis, it was the mainstream. Isaac Newton gestured toward it. Christian Huygens built his wave theory of light on top of it. James Clerk Maxwell, whose equations in the 1860s unified electricity, magnetism, and light into a single framework of breathtaking elegance, assumed the ether was the medium through which his electromagnetic waves propagated. Maxwell's equations produced something that stopped physicists cold. When you solved them fully, they spat out a precise number: the speed of electromagnetic radiation in a vacuum, not a range, a single fixed number. What his equations could not answer was, fixed relative to what? The speed of sound is fixed relative to the air it moves through. A source moving toward you compresses the sound waves and raises the pitch. A source moving away stretches them and lowers it. This is the Doppler effect, and it works because sound has a medium, the air, that defines a reference frame. The ether was supposed to do the same thing for light. Earth, moving through the ether as it orbited the sun, should experience an ether wind. Light moving against that wind should travel slightly slower than light moving with it. The difference would be small, but measurable. In 1887, Albert Michelson and Edward Morley set out to measure it. Michelson had already spent years designing an instrument of almost obsessive precision, the interferometer. It worked by splitting a beam of light into two perpendicular paths, bouncing each path off a mirror and recombining them. Because the two paths traveled in different directions relative to the hypothetical ether wind, they should arrive back slightly out of phase. And that phase difference would appear as a shift in the interference pattern, a set of bright and dark fringes that Michelson could measure with extraordinary sensitivity. The entire apparatus was mounted on a massive sandstone slab floating in a pool of liquid mercury to eliminate vibrations. It was, for its era, one of the most sophisticated experimental setups ever constructed. They ran the experiment. They rotated the apparatus. They measured at different times of day and different times of year as Earth shifted its direction of motion through the supposed ether. The fringe shift they expected was small, roughly 4/100ths of the fringe spacing. Their instrument could detect shifts as small as 1/100th of a fringe. The result they got, effectively zero. The ether wind was not there. No matter the direction of measurement, no matter the season, no matter the orientation of the apparatus, light arrived with no detectable difference in speed. The experiment was so definitive and so shocking that Michelson himself reportedly said it was a failure. He had gone looking for the ether and found nothing. The physics community spent the next 18 years in various states of denial, recalculation, and theoretical rescue attempts. George Fitzgerald proposed that physical objects actually contract in the direction of motion through the ether, precisely enough to cancel out the expected measurement. Hendrik Lorentz independently derived the same mathematics, producing what became known as the Lorentz transformations. Both men were groping toward the right answer with the wrong conceptual framework. They kept the ether and adjusted the objects moving through it. What they needed to do, what no one was yet prepared to do, was discard the ether entirely and accept the radical implication of Michelson and Morley's null result. Light does not need a medium, and its speed is not fixed relative to any medium. It is fixed relative to every observer, regardless of how fast that observer is moving. This is the statement that breaks intuition. It is not that the speed of light is very fast, it is that the speed of light is the same for everyone. A spacecraft moving at half the speed of light toward a star and a spacecraft moving at half the speed of light away from that same star will both measure the light from that star arriving at exactly the same speed. 299,792,458 meters per second. Not faster for one and slower for the other. Identical, always. In everyday human experience, speeds add and subtract. A baseball thrown at 40 meters per second from a car moving at 30 meters per second arrives at 70 meters per second. This is Galilean relativity, and it works perfectly for everything humans have ever directly experienced. But it is not the full picture. It is an approximation that holds so well at low velocities that our senses and our intuition were never equipped to notice where it breaks down. It breaks down at velocities that are a significant fraction of the speed of light. And the place where it breaks down is precisely the place where Maxwell's equations and the Michelson-Morley experiment, and ultimately Einstein's special relativity, all converge on the same conclusion. In 1905, Albert Einstein was 26 years old and working as a patent clerk in Bern, Switzerland. He had no laboratory, no university position, no direct access to the experimental data accumulating at the edges of classical physics. What he had was an extraordinary capacity for what he called thought experiments, Gedankenexperimente, and a willingness to follow the logic of physics wherever it led, even when it led somewhere that shattered common sense. The question he had been carrying since he was 16 years old was deceptively simple. What would you see if you could ride alongside a beam of light? Classical physics had an answer, and it was deeply uncomfortable. If you traveled at the speed of light next to a light wave, you should see it frozen in space, an oscillating electromagnetic field suspended motionless beside you. But Maxwell's equations did not permit a stationary electromagnetic wave. They had no solution that described light standing still. The two frameworks, Newtonian mechanics and Maxwellian electromagnetism, were in direct, irreconcilable contradiction. One of them had to give. Einstein gave up Newtonian absolute time and absolute space. He kept Maxwell. His 1905 paper on the electrodynamics of moving bodies began not with experiment, but with two postulates. First, the laws of physics are identical in all inertial reference frames, any frame moving at constant velocity. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these two premises alone, using only algebra, Einstein derived the Lorentz transformations, the same equations Fitzgerald and Lorentz had found by trying to save the ether, and showed that they were not a physical quirk of matter contracting through a medium. They were a geometric property of spacetime itself. Time dilation was not a mechanical effect. Length contraction was not a compression of matter. They were the inevitable consequence of living in a universe where the speed of light is invariant. Space and time were not independent, absolute stages on which events played out. They were woven together into a single four-dimensional fabric, space-time, and the way any observer experienced the dimensions of that fabric depended on how fast they were moving through it. The faster you move through space, the slower you move through time. This is not metaphor. Atomic clocks flown on aircraft run measurably slower than identical clocks left on the ground. GPS satellites, orbiting at roughly 14,000 kilometers per hour, accumulate a relativistic time discrepancy of roughly 7 microseconds per day relative to ground-based clocks. That discrepancy is not theoretical noise, it is a real operational engineering problem. Without corrections built into the GPS system to account for special and general relativity simultaneously, position errors would accumulate at roughly 10 kilometers per day, rendering the entire system useless within hours. Every time a GPS receiver in a phone or aircraft computes a position, it is implicitly relying on Einstein's 1905 paper. Special relativity is not a hypothesis awaiting stronger confirmation. It has been tested by every precision experiment available to modern physics, confirmed in particle accelerators, atomic clocks, astronomical observations, and the daily function of global navigation infrastructure. Its predictions are accurate to better than 1 part in 10 billion in some experimental contexts. The framework is not in question. What it tells us about the speed of light is unambiguous. The limit is not technological. The equations do not contain a footnote that says, unless a sufficiently advanced civilization finds an engineering solution. The invariance of the speed of light and the relativistic behavior of mass and energy are consequences of the geometric structure of the universe. To exceed the speed of light with a massive object would require not a better rocket, it would require a different universe. But physics rarely closes a door without opening a window, and the same equations that forbid faster than light travel for massive objects contain, buried in their geometry, a set of possibilities that no one in 1905 was prepared to take seriously. They involve not moving faster through space, but bending space itself. Space is not empty. This is not a philosophical statement or a poetic abstraction. It is one of the most rigorously confirmed findings of 20th century physics, and it changes everything about how we must think of the universe and about what it would mean to move through it at extreme velocities. The vacuum of space, at the quantum level, is a seething, roiling medium of energy. Virtual particles flicker in and out of existence on timescales so short, they fall below the threshold of direct detection. Pairs of matter and antimatter born from pure energy and annihilating back into it before any measuring instrument can catch them in the act. This is not a theoretical convenience. The Casimir effect, a measurable attractive force between two uncharged metal plates placed nanometers apart in a vacuum, is direct experimental evidence that the quantum vacuum carries real physical energy. The plates are pushed together by the difference in vacuum energy between the space inside them and the space outside. You can measure the force with a sensitive enough instrument. The vacuum pushes back. This matters for the question of faster-than-light travel because it places a physical actor in what we casually call empty space. Any object moving through the quantum vacuum at relativistic velocities interacts with it. And the interactions are not gentle. But before reaching the quantum scale, the obstacle presented by classical relativity alone is already sufficient to make the problem vivid. Consider the energy budget of acceleration. At low velocities, anything humans have achieved with chemical rockets, the Newtonian approximation holds with extraordinary accuracy. The kinetic energy of a moving object is 1/2 its mass multiplied by its velocity squared. A spacecraft with a mass of 1,000 kilograms moving at 10 kilometers per second carries roughly 50 billion joules of kinetic energy. That is approximately the energy released by 12 tons of TNT. It is an enormous amount by everyday standards, and it represents the practical ceiling of what chemical propulsion can deliver. Now apply relativistic mechanics. As velocity increases toward the speed of light, the equation for kinetic energy changes. It is no longer the clean Newtonian formula. The relativistic kinetic energy of a moving object is its total energy minus its rest energy, the difference between the Lorentz factor multiplied by the rest mass times the speed of light squared and the rest mass times the speed of light squared. The Lorentz factor, and the term that captures how severely time, length, and mass are distorted at a given velocity, grows slowly at first. At 10% of light speed, it is approximately 1.005. Barely distinguishable from 1. At 50% of light speed, it reaches approximately 1.15, still modest. At 90%, it rises to roughly 2.3. At 99%, it exceeds 7. At 99.9%, it passes 32. At 99.99%, it surpasses 220. What this means in practice: at 99% of the speed of light, a spacecraft with the mass of a small car, roughly 1,000 kilograms, would carry a kinetic energy of approximately 1.9 times 10 to the power of 20 joules. To place that number in human terms, the total annual energy consumption of the entire United States, every power plant, every vehicle, every building, every device, amounts to roughly 4 times 10 to the power of 19 joules per year. Accelerating that small car to 99% of light speed would require nearly 5 times the total annual energy output of the United States, delivered entirely to a single 1,000 kilogram object, not over a year. As a total energy investment, a crewed spacecraft capable of sustaining human life, life support, navigation, radiation shielding, communication systems, structural integrity under acceleration, would not mass 1,000 kilograms. Current crewed spacecraft mass in the range of tens of thousands of kilograms. The International Space Station masses approximately 420,000 kilograms. Scaling the energy requirements accordingly does not produce a large number. It produces a number that exceeds the total energy output of the Sun over meaningful timescales. The Sun radiates approximately 3.8 times 10 to the power of 26 joules every second. Every second, without pause, the Sun converts roughly 4 million metric tons of its own mass into pure energy through nuclear fusion. It has been doing this for 4.6 billion years and will continue for approximately another 5 billion. The total energy output of the Sun over its entire 10 billion year lifespan is staggering beyond any human frame of reference. And even a fraction of that energy budget, applied entirely to a single spacecraft, would not be enough to push a crewed vehicle to the speed of light. because as the vehicle approaches that limit, the energy required per additional meter per second of velocity diverges. It does not plateau. It does not asymptote at some achievable threshold. It grows without bound. No star, no galaxy, no known physical process in the observable universe produces infinite energy. The problem runs deeper still when you introduce the question of fuel. Every propulsion system humans have ever built or seriously proposed operates on a fundamental principle. It throws something backward to push the vehicle forward. Chemical rockets throw hot exhaust gases. Ion thrusters throw accelerated ions. Even a theoretical photon rocket, which would generate thrust by emitting photons directly, throws photons backward. In every case, the fuel required to accelerate a vehicle is itself part of the vehicle's mass at the start of the journey, and that fuel must also be accelerated. This is the tyranny of the rocket equation, formalized by Konstantin Tsiolkovsky in 1897. The ratio of a rocket's initial mass, fully fueled to its final mass, after the fuel is spent, must increase exponentially with the desired change in velocity. At non-relativistic speeds, the rocket equation is already punishing. The Saturn V rocket that carried the Apollo missions to the moon had a launch mass of approximately 2.8 million kilograms. The payload delivered to the lunar surface was roughly 15,000 kilograms. The ratio of total mass to final payload was nearly 190 to 1. For a mission to the moon, a target 384,000 kilometers away. Proxima Centauri is 4.2 light-years away. That is approximately 40 trillion kilometers. The moon, by comparison, is so close that light reaches it in 1.3 seconds. Light takes 4.2 years to reach Proxima Centauri. At the velocities achievable by chemical propulsion, the fuel-to-payload ratio required for a one-way trip to the nearest star reaches numbers that exceed the total mass of matter in the observable universe, not by a small margin. By many orders of magnitude. Nuclear propulsion changes the arithmetic, but does not resolve it. A nuclear pulse drive, the concept explored in the 1950s and 1960s under Project Orion, which proposed detonating nuclear bombs behind a spacecraft to generate thrust, could theoretically achieve velocities between 3 and 10% of the speed of light. At 3% of light speed, a journey to Proxima Centauri would take approximately 140 years. At 10%, roughly 42 years. These timescales are at the outer edge of a human lifetime, and they assume a perfectly functioning spacecraft, no navigational errors, no material degradation over decades of interstellar travel, and a destination that offers something worth the journey. At 10% of light speed, relativistic effects are still modest. The Lorentz factor is approximately 1.005. Time dilation would be barely perceptible, but the collision problem becomes acute. Interstellar space is not perfectly empty. It contains gas, dust, and occasional larger particles. At 10% of light speed, a dust grain with a mass of 1 milligram strikes with the energy of a small explosive. At velocities approaching the speed of light, even the diffuse hydrogen atoms of the interstellar medium become a lethal radiation field. A spacecraft traveling at 90% of light speed would encounter interstellar protons as if they were a beam of particles in an accelerator, delivering ionizing radiation doses to any crew or sensitive electronics that no known shielding material could fully neutralize. The engineering challenges multiply faster than the velocity does. Theoretical physicists, confronted by the hard ceiling of special relativity, did not abandon the question. They went around it. If you cannot accelerate a massive object through space faster than light, the question becomes, what about space itself? Einstein's general theory of relativity, published in 1915, extended special relativity to include gravity and acceleration. Its central insight was that mass and energy curve spacetime, the four-dimensional fabric whose geometry special relativity had revealed. Gravity is not a force transmitted through space. It is the curvature of spacetime caused by mass, and objects moving through that curved spacetime follow the straightest possible paths, geodesics, that appear, to an outside observer, as curved trajectories. General relativity permits something special relativity does not. The metric of spacetime, the mathematical description of its geometry, can itself change. Space can expand. space can contract. The expansion of the universe, first observed by Edwin Hubble in 1929 and confirmed by decades of subsequent measurement, is precisely this. The metric of space is growing, carrying galaxies apart from one another at velocities that, in some regions of the observable universe, exceed the speed of light. No galaxy is moving through space faster than light. Space itself is expanding, and the galaxies are carried with it. This distinction between motion through space and motion of space is the thread that theoretical physicists have pulled for decades. If space can expand faster than light carries information, can it be deliberately manipulated? Can a region of space be contracted in front of a spacecraft and expanded behind it, effectively surfing a wave of space-time geometry at any desired velocity? In 1994, a physicist named Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity that demonstrated, within the mathematics of general relativity, that such a space-time geometry was not forbidden by the equations. The Alcubierre metric described a bubble of flat space-time surrounded by a region of contracted space ahead and expanded space behind. Inside the bubble, no object would be moving faster than light relative to its local space-time. The space-time itself would be doing the moving. The equations did not say it was impossible. They said something almost more daunting. They specified what it would cost. Miguel Alcubierre was a Mexican physicist working on his doctorate at the University of Wales in Cardiff when he published what would become one of the most cited and most debated papers in the history of theoretical physics. The year was 1994. The paper was 9 pages long. Its title was The Warp Drive, Hyperfast Travel Within General Relativity. And it did something no one had done rigorously before. It took the mathematics of Einstein's field equations and constructed from within them a metric, a precise geometric description of space-time, that would allow a vessel to travel between 2 points faster than light would cover the same distance through undistorted space. The idea was elegant in its structure. The Alcubierre metric describes a region of flat, undistorted space-time, the bubble, inside which a spacecraft sits. The spacecraft itself never moves relative to its immediate local space-time. It experiences no acceleration, no g-forces, no time dilation in the way a relativistically accelerating vessel would. Inside the bubble, the laws of physics behave exactly as they do in any inertial frame. The crew would feel nothing unusual. Around the bubble, however, space-time itself is being deformed. Space contracts sharply in front of the bubble, drawing the destination closer. Space expands behind it, pushing the origin point away. The bubble, and everything inside it, is effectively surfing a wave of space-time geometry, carried forward not by any internal thrust, but by the deformation of space itself. Because no object inside the bubble is moving through space faster than light, special relativity is not violated. The constraint Einstein placed on motion through spacetime does not apply to the motion of spacetime itself. General relativity has no speed limit for the expansion or contraction of space. The universe demonstrated this from its first moments. In the period of cosmic inflation immediately following the Big Bang, regions of space were driven apart at rates enormously exceeding the speed of light. Galaxies at the edge of the observable universe are currently receding from us, at velocities exceeding the speed of light. Not because they are moving through space that fast, but because the space between us and them is expanding. Alcubierre's insight was to ask whether the same principle could be harnessed deliberately and directionally. The mathematics said yes. The physics said, at what cost? The first and most fundamental problem is energy. To sustain the Alcubierre metric, to maintain the warped spacetime geometry around the bubble, requires a quantity of energy with a specific and deeply problematic sign. It requires negative energy, not a very small amount of energy, not zero energy. Negative energy, a quantity of energy less than the vacuum, less than nothing, in the framework of quantum field theory. Negative energy is not entirely fictional. The Casimir effect, described in Act 3, produces a measurable region of energy density slightly below that of the vacuum between two closely spaced conducting plates. The effect is real, reproducible, and well understood, but the magnitudes involved are extraordinarily small, relevant at the nanometer scale, produced by the geometry of boundary conditions in quantum electrodynamics. The amount of negative energy required to sustain an Alcubierre bubble of any practical size is, by contrast, grotesque. Alcubierre's original 1994 calculation estimated the negative energy required to move a bubble of approximately 100 meters in diameter at 10 times the speed of light. The result was a number with a mass energy equivalent roughly equal to the total mass energy of the planet Jupiter, but negative. A negative Jupiter. The entire mass energy of a gas giant, converted to its equivalent in negative energy, consumed to sustain a single warp bubble for a single journey. Subsequent refinements of the metric developed by Harold White at NASA's Johnson Space Center in the early 2010s suggested that modifications to the geometry of the bubble, making it thinner and oscillating, could dramatically reduce the energy requirement. White's calculations indicated a reduction of many orders of magnitude, potentially bringing the required energy into a range that sounded in relative terms almost manageable. His figures suggested the negative energy equivalent of a mass roughly that of the Voyager spacecraft. This generated significant media coverage and gave rise to headlines about NASA working on a warp drive. The actual situation was considerably more constrained. White's team was conducting tabletop interferometry experiments, not warp field tests, but precision measurements of space-time geometry at extremely small scales, to look for any detectable effect. The experimental results produced no confirmed detection of a warp field. The theoretical reduction in energy requirements, while mathematically valid within a specific set of assumptions, did not resolve the more fundamental problem. No known physical process produces negative energy at any scale remotely approaching what even the most optimistic warp drive estimates require. The vacuum fluctuations that produce the Casimir effect are a quantum phenomenon. They cannot be simply scaled up. There is no engineering pathway, not even a speculative one grounded in known physics, that connects the nanometer-scale negative energy density of a Casimir cavity to the planetary-scale negative energy reservoir that a warp drive demands. The gap is not a matter of better materials or more efficient geometry. It is a gap between what quantum field theory permits to exist and what warp drive mathematics requires to function. The second fundamental problem is causality. A faster-than-light transport mechanism, if it existed, would not merely allow rapid travel. It would, in the framework of special relativity, allow travel backward in time. This is not a philosophical concern. It is a direct mathematical consequence of the Lorentz transformations. In relativity, the sequence of events, which happens before which, is not absolute. It depends on the reference frame of the observer. For events separated by a space-like interval, meaning that no signal traveling at or below the speed of light could connect them, different observers in different reference frames will disagree on which event happened first. A faster-than-light signal sent from point A to point B in one reference frame can, in a different reference frame moving relative to the first, appear to arrive at B before it left A. String two faster-than-light journeys together, the first in one reference frame, the second in a frame moving relative to the first, and the mathematics allows a traveler to arrive at a destination before they departed. This is the closed time-light curve problem, and it is not a quirk of the Alcubierre metric specifically. It applies to any physically realizable faster-than-light mechanism. Stephen Hawking formalized this concern in what he called the chronology protection conjecture, the hypothesis that the laws of physics conspire to prevent the formation of closed time-light curves, and that any attempt to create a faster-than-light transport mechanism will be self-defeating, destroyed by the quantum effects that arise precisely at the moment it would otherwise succeed. The conjecture remains unproven, but the evidence from quantum field theory in curved space-time, the study of how quantum mechanics behaves in the presence of gravitational fields, suggests that the energy conditions required by warp drives and traversable wormholes are precisely the energy conditions that quantum field theory forbids at macroscopic scales. The universe appears to be remarkably consistent in closing these doors. Traversable wormholes present the same accounting problem from a different angle. A wormhole, a topological shortcut connecting two distant regions of spacetime, was first described mathematically by Einstein and Nathan Rosen in 1935 as a solution to the field equations of general relativity. The Einstein-Rosen bridge, as it was initially called, appeared to connect two regions of spacetime through a throat of compressed geometry. But the original solution described a wormhole that was not traversable. It pinched off and collapsed faster than any signal, let alone any material object, could pass through it. The collapse timescale was shorter than the light-crossing time of the throat. Kip Thorne and his colleagues at Caltech, working in the late 1980s partly in response to a question posed by Carl Sagan for his novel Contact, demonstrated that a traversable wormhole would require exotic matter, material with negative energy density, threaded through its throat to hold it open against gravitational collapse. The exotic matter would need to be distributed throughout the throat at sufficient density to counteract the implosive tendency of the geometry. The energy conditions involved are the same ones that appear in the Alcubierre metric and the same ones that quantum field theory strongly disfavors at any practical scale. In 2018, a new class of wormhole solutions entered the literature. Physicists Juan Maldacena and Alexei Malekin, building on earlier work connecting wormhole geometry to quantum entanglement, the ER equals EPR conjecture, proposed by Maldacena and Leonard Susskind in 2013, described a type of wormhole that would not require exotic matter with negative energy density. The construction involved charged particles and specific conditions in certain theoretical spacetimes. The traversal times, however, were calculated to be longer than travel through ordinary space by the same route. A wormhole that takes longer to traverse than going around it does not solve the faster-than-light problem. It was a profound result for theoretical physics and for the deep relationship between geometry and quantum information, but it was not a shortcut. The pattern, across 30 years of serious theoretical investigation, is consistent. Every approach that appears to offer a path around the speed of light, warp drives, traversable wormholes, tachyons, quantum tunneling, either requires energy conditions that known physics cannot supply, produces causal paradoxes that the structure of spacetime appears to forbid, or delivers traversal times that are no improvement over conventional travel. The universe does not appear to leave these doors merely locked. It appears to have removed the hinges. And yet the investigations were not wasted, because in examining the edges of what general relativity permits, physicists stumbled onto a connection so unexpected, so structurally deep, that it redirected an entire generation of theoretical research away from warp drives and towards something far stranger. The geometry of spacetime and the behavior of quantum information are not separate subjects. They are, at some fundamental level, the same subject. And that realization cracked open a question that no one in 1994 was asking. What if the structure of space itself is not the stage on which physics plays out, but the consequence of it? The question of faster-than-light travel, stripped of every engineering fantasy and every optimistic theoretical footnote, ultimately arrives at a place that is simultaneously more restrictive and more astonishing than any warp drive concept. It arrives at the structure of information itself, at what the universe permits to be known, transmitted, and experienced across the distances that separate everything from everything else. Quantum mechanics introduced in the early 20th century, a phenomenon so counterintuitive that Einstein spent the last 3 decades of his life convinced it concealed a flaw in the theory. He called it spooky action at a distance. The formal term is quantum entanglement. 2 particles, prepared together in a correlated quantum state and then separated by any distance, meters, kilometers, or in principle light years, retain a connection such that a measurement performed on one instantly determines the outcome of a measurement on the other. Not after a delay proportional to the distance between them. Instantly. The correlation is immediate, regardless of separation. Einstein, Boris Podolsky, and Nathan Rosen formalized their discomfort with this in 1935 in what became known as the EPR paper. Their argument was that if quantum mechanics was complete, if the instantaneous correlations were real and not merely the revelation of pre-existing hidden properties, then quantum mechanics violated locality, the principle that physical influences cannot travel faster than light. Something, they argued, had to be missing. Some hidden variable, some additional information carried by the particles from the moment of their creation had to be determining the outcomes in advance. In 1964, physicist John Bell derived a set of mathematical inequalities, Bell's inequalities, that made the distinction between hidden variable theories and genuine quantum non-locality experimentally testable. If hidden variables were responsible, the correlations between measurements on entangled particles could not exceed a specific statistical bound. If quantum mechanics was correct, and the correlations were genuinely non-local, the bound would be violated. The test was not a thought experiment, it was a measurement waiting to be made. Alain Aspect and his team at the Institut d'Optique in Paris performed the decisive experiment in 1982. They produced pairs of entangled photons and measured their polarizations at detectors separated by sufficient distance, with measurement settings changed rapidly enough that no signal traveling at light speed could carry information from one detector to the other before each measurement was completed. Bell's inequalities were violated, clearly, reproducibly. The result has since been confirmed in dozens of increasingly stringent experiments, closing one potential loophole after another. The detector efficiency loophole, the locality loophole, the freedom of choice loophole. The most rigorous tests, performed in the 2010s with detectors separated by hundreds of kilometers and random number generators determining measurement settings in real time, produced the same result every time. Quantum entanglement is real. The correlations are genuinely non-local. Hidden variable theories of the local variety are experimentally ruled out, and yet, no information travels faster than light through entanglement. This is not a failure of the experiments or a limitation of current technology. It is a structural feature of quantum mechanics itself, built into the theory at the deepest level. When you measure an entangled particle, the outcome you get is random. You cannot control it. Your partner at the other detector also gets a random outcome. Only when you compare your results through a classical channel, a phone call, a radio signal, any communication limited to the speed of light or below, do you discover that your random outcomes were correlated. The correlation itself cannot be used to send a message, because neither party has any control over their individual measurement results. The non-locality is real, but it is, in a precise technical sense, uncontrollable. And uncontrollable correlations cannot carry information. This is not a loophole waiting to be exploited. The no-communication theorem is a mathematically proven result of quantum mechanics. It states that no measurement performed on one half of an entangled system can be used to transmit information to the observer of the other half faster than light. The proof does not rest on engineering limitations. It rests on the linearity of quantum mechanics and the statistical structure of measurement outcomes. As long as quantum mechanics is correct, and it is the most precisely tested theory in the history of science, with predictions confirmed to better than 1 part in 10 billion in some experiments. Faster-than-light communication through entanglement is not merely difficult. It is mathematically forbidden. The universe appears to have been constructed with extraordinary care around a single constraint, causality. The principle that causes precede effects. That information about an event cannot reach any observer before that event has occurred. Special relativity encodes this in the geometry of spacetime through the concept of the light cone. Every event in spacetime has a future light cone, the region of spacetime that can be influenced by that event, and a past light cone, the region from which information could have reached that event. Outside these cones lies the region of space-like separation where no causal connection is possible. The speed of light is not merely a velocity limit. It is the boundary of causality itself. Every attempt to exceed it, whether through relativistic propulsion, warp geometry, wormhole topology, or quantum non-locality, runs into the same wall, expressed in different mathematical languages. The wall is not technological, it is causal. The universe does not permit effects to precede causes. And since faster-than-light travel, in the framework of special relativity, is mathematically equivalent to time travel into the past, the prohibition on faster-than-light signaling and the prohibition on causal paradoxes are the same prohibition. This does not mean the universe is small or that humanity is imprisoned. The observable universe, the sphere of space from which light has had time to reach us in the 13.8 billion years since the Big Bang, has a radius of approximately 46 billion light-years. Not 13.8 billion, because space has been expanding throughout that time. carrying the sources of the oldest light we can detect to distances far beyond where they were when that light was emitted. 46 billion light-years in every direction. That volume contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars, the vast majority of which we now know host planetary systems. The Kepler Space Telescope alone confirmed the existence of more than 2,500 exoplanets during its operational lifetime, and statistical analyses of its data suggest that virtually every star in the Milky Way hosts at least one planet. The galaxy contains somewhere between 100 billion and 400 billion stars. The number of planets in the observable universe alone is not meaningfully distinguishable from infinity at any human scale of comprehension. The nearest of those worlds, the planets orbiting Proxima Centauri, including Proxima Centauri b, confirmed in 2016 and situated in or near the star's habitable zone, sits 4.2 light-years away. At the velocities achievable by the most advanced propulsion concepts grounded in near-term physics, laser sail systems like those envisioned by Breakthrough Starshot, which proposes accelerating gram-scale probes to 20% of light speed using a ground-based laser array, a flyby of the Proxima system would take approximately 20 years. No deceleration, no orbital insertion, a brief passage through the system at a fifth of the speed of light, with instruments collecting data for a matter of hours before the probe recedes into darkness on the far side. 20 years to the nearest star, with no ability to stop, using a technology that does not yet exist, but is physically plausible. A round trip with any kind of meaningful data return, accounting for the 4-year signal delay at light speed, would span a human lifetime. That is the actual frontier, not warp drives. Not wormholes. Laser sails the size of a meter, gram-scale payloads, and a 20-year transit to a target 4 light-years away. The stars are not unreachable in principle. They are unreachable in the way that the bottom of the Mariana Trench was unreachable in the 15th century, not because the laws of physics forbid it, but because the engineering required is so far beyond current capability that the gap between aspiration and execution spans generations, perhaps centuries. The difference is that the ocean floor imposes no fundamental physical limit on depth. The stars impose one on speed. In 1977, the twin Voyager spacecraft left Earth carrying gold-plated phonograph records containing sounds and images selected to represent life and culture on this planet. Greetings in 55 languages, music from every continent, the sound of surf, wind, and thunder, the cry of a newborn. The record was not designed as a practical communication device. It was a gesture, an acknowledgement that the universe is large, that we are small, and that the act of reaching outward, even slowly, even over timescales that exceed individual human lives, is itself meaningful. Voyager 1 is now in interstellar space, more than 23 billion kilometers from the Sun, still transmitting at 40 watts, roughly the power of a dim light bulb, across a distance so great that its signal, traveling at the speed of light, takes more than 22 hours to reach the antennas of the deep space network on Earth. The spacecraft moves at 17 kilometers per second and will not reach the distance of the nearest star system for approximately 73,000 years. It is the fastest object humanity has ever launched from Earth. It is moving at less than 1/6,000th of the speed of light, and in the silence between those numbers, between 17 kilometers per second and 299,000 kilometers per second, lies the full weight of the problem. Not as a defeat, as a dimension. The universe is not obligated to be traversable on human timescales. It was not designed around our lifespans or our ambitions. The laws of physics are what they are, and they are consistent, and they are knowable, and that knowability, the fact that a species of terrestrial primates has spent a century unraveling the geometric structure of spacetime through mathematics and experiment, is by any measure the more extraordinary story. The speed of light is the universe's signature. Every photon that reaches your eye from a distant star left that star years, centuries, or millennia ago. You are not seeing the star. You are seeing its past. The night sky is a time machine pointing backward, and the speed of light is the conversion factor between distance and history. Every constellation is an archive. Every galaxy is a message from a universe that existed long before anything on Earth had eyes to receive it. That message travels at exactly 299,792,458 meters per second, not 1 meter per second faster. There is a particular kind of clarity that comes from a closed door. Not the frustration of a locked room, but the orientation that a wall provides. The way a boundary, once understood, defines the shape of everything on this side of it. The speed of light is that kind of boundary. It does not diminish the universe. It describes it. And in describing it, it tells us something precise and irreplaceable about what kind of universe we actually inhabit, rather than the one we might have preferred. For most of human history, the speed of light was not known to be finite. The ancient Greeks debated whether vision was instantaneous. Galileo attempted to measure the speed of light in the early 17th century by uncovering lanterns between hilltops separated by a few kilometers. The delay, if any existed, was far too small for human reaction times to detect. The first credible evidence that light had a finite speed came in 1676, when Danish astronomer Ole Romer noticed discrepancies in the timing of the eclipses of Io, one of Jupiter's moons. When Earth was moving toward Jupiter in its orbit, the eclipses came slightly early. When Earth was moving away, they came slightly late. Romer correctly interpreted this as the travel time of light across the changing distance between Earth and Jupiter. His estimate, approximately 220,000 kilometers per second, was remarkably close to the true value for an observation made with the instruments of the 17th century. What Romer had discovered was not merely a number. He had discovered that the universe has a communication delay built into its architecture. Every observation of a distant object is an observation of the past. The light arriving at Romer's telescope from Jupiter's moons had left its source minutes earlier. The light arriving at your eye from the moon left the lunar surface 1.3 seconds ago. From the sun, 8 minutes and 20 seconds. From Proxima Centauri, 4.2 years. From the Andromeda Galaxy, 2.5 million years. From the most distant galaxies detectable by the James Webb Space Telescope. Objects whose light was emitted when the universe was less than 500 million years old, more than 13 billion years. The night sky is not a simultaneous snapshot of the universe. It is a layered fossil record, each shell of distance corresponding to a different era in cosmic history. When astronomers study the large-scale structure of the universe, the distribution of galaxies, the properties of galaxy clusters, the statistical patterns in the cosmic microwave background, they are doing geology. They are reading strata. The further they look, the earlier the epoch they are sampling. The cosmic microwave background radiation, the oldest light in the universe, is a photograph of the universe at 380,000 years after the Big Bang, when the cosmos had cooled sufficiently for electrons and protons to combine into neutral hydrogen for the first time, and the universe became transparent to light for the first time. That photograph is plastered across the entire sky, in every direction, at a temperature of 2.725 Kelvin, just barely above absolute zero, uniform to 1 part in 100,000, with tiny fluctuations that seeded every galaxy, every star, every planet that came after. The speed of light made that photograph possible. Without a finite speed of light, there would be no look-back time, no cosmic archaeology, no stratified record of universal history readable from a single vantage point. The finite speed of light is not an obstacle to understanding the universe. It is the instrument through which the universe's history is legible. This reframing is not rhetorical consolation. It reflects a genuine and profound feature of how knowledge about the cosmos is structured. The Hubble Space Telescope's deep field images, long exposures of tiny patches of sky that revealed thousands of galaxies in regions that appeared empty to the naked eye, were possible precisely because light from those galaxies had been traveling for billions of years to reach the telescope's detector. The depth of those images is temporal depth as much as spatial depth. Each galaxy at a different distance is a galaxy at a different point in time. The sequence of galaxy morphologies across cosmic time, the transition from irregular, clumpy, actively star-forming galaxies in the early universe to the more settled elliptical and spiral structures of the present, is a developmental history of cosmic structure, readable because light travels at a fixed, finite speed and has been accumulating in transit since the universe began. The James Webb Space Telescope, launched in December 2021 and achieving full scientific operations in 2022, has pushed this archaeology to its current frontier. Its infrared detectors are tuned to observe light that left its sources when the universe was less than 300 million years old, the epoch of the first stars and the first galaxies, a period known as cosmic dawn. The light from those objects has been traveling for more than 13 billion years. It has been stretched by the expansion of the universe from ultraviolet and visible wavelengths into the infrared during its journey. Webb sees it not because it has overcome any fundamental limit, but because it is exquisitely sensitive to the specific wavelengths that the finite speed of light and cosmic expansion have delivered to us here, now, at this point in the universe's history. We did not choose when to exist. We exist 13.8 billion years after the Big Bang in a galaxy that formed roughly 10 billion years ago, on a planet that formed 4.5 billion years ago, at a moment when the technology to detect infrared light from the universe's first galaxies has existed for approximately 3 years. The coincidence is not a coincidence. It is a condition. And the light that makes all of this knowledge possible has been in transit at exactly 299,792,458 meters per second for longer than the Earth has existed. The scale of what that implies deserves to sit without being rushed past. A photon detected by the James Webb Space Telescope in 2023, originating from a galaxy designated JD's GS Z13-0 at a redshift of 13.2, was emitted approximately 320 million years after the Big Bang. The universe at that moment was a fraction of its current size. The galaxy that emitted it no longer exists in anything like its original form. It has evolved, merged, transformed over 13 billion years into something unrecognizable. The photon traveled through the expanding universe, stretching as it went, navigating around gravitational wells, surviving the transition through epochs of ionization and structure formation, crossing distances that expanded beneath it as it moved, and arrived at a mere 68 square meters in area, cooled to 40 Kelvin in the L2 orbit, 1.5 million kilometers from Earth. That photon's journey lasted longer than the age of the solar system. Nothing about that journey required faster-than-light travel. The science it enabled, the identification of the galaxy, the measurement of its redshift, the inference of its stellar mass and star formation rate, the reconstruction of conditions in the universe at cosmic dawn was accomplished entirely within the constraints of a universe governed by a finite speed of light. The limit was not the obstacle. The limit was the ladder. The human relationship with cosmic distance is, at its core, a relationship with time. To look outward is to look backward. To extend observational reach is to extend temporal reach. Every improvement in telescope sensitivity, in detector technology, in signal processing, every incremental engineering achievement in the history of astronomy has been an achievement in reading deeper into the past, not in overcoming the speed of light, but in using it more completely. The universe has been broadcasting its history at the speed of light since 380,000 years after its origin. The question was never whether we could travel to receive it. The question was whether we could build instruments sensitive enough to read what was already arriving. On that question, the trajectory is unambiguous. In 1845, the most powerful telescope on Earth was the 72-inch Leviathan of Parsonstown in Ireland, which revealed the spiral structure of certain nebulae for the first time. In 1929, Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson to establish that those nebulae were independent galaxies and that they were receding from us at velocities proportional to their distance, the observational foundation of modern cosmology. In 1990, the Hubble Space Telescope was placed in low Earth orbit, and despite an initial mirror flaw corrected in 1993, transformed our picture of the universe's depth, age, and diversity of structure. In 2022, the James Webb Space Telescope showed us the universe's first light. Each of these instruments operated entirely within the speed of light constraint. Each extracted knowledge from the photons that were already here, already arriving, already carrying information about the universe's history encoded in their wavelengths, their polarizations, their arrival times. The speed of light did not prevent any of this. It made all of it possible. There is a further dimension to this that is rarely articulated outside of specialist contexts. The finite speed of light is not merely a constraint on travel or communication. It is the reason the universe has a horizon at all, a boundary beyond which, no matter how powerful the telescope, no information can reach us. The cosmological horizon is the surface beyond which the expansion of space has carried objects so far that light from them has not had time to reach us since the Big Bang. The universe beyond that horizon is not empty. It is not absent. It is simply causally disconnected from us, not because of any physical barrier, but because 13.8 billion years of light travel time in an expanding universe defines a finite sphere of observability. That sphere contains, as noted, approximately 2 trillion galaxies. If even a tiny fraction of those galaxies host planets with conditions suitable for complex chemistry, the number of such worlds is incomprehensibly large. The Drake equation, formulated by Frank Drake in 1961 as a framework for estimating the number of technologically communicating civilizations in the galaxy, is not a calculation that produces a reliable answer. Its parameters are too uncertain. But it is a map of the question, and the question it maps has grown more tractable with every passing decade of exoplanet research. We now know that planets are not rare. We now know that organic chemistry operates throughout the galaxy. We now know that liquid water, once considered a peculiarity of Earth, is abundant, locked in the subsurface oceans of Europa and Enceladus, present in the ancient geology of Mars, reigning as droplets in the atmosphere of Venus in conditions that, billions of years ago, may have been hospitable. The speed of light will not prevent us from knowing whether life exists elsewhere. It will govern how long it takes for that knowledge to arrive. A signal from a civilization 100 light-years away transmitted today will reach Earth in 100 years. A response transmitted immediately upon receipt will return 100 years after that. A dialogue spanning 3 exchanges will take 600 years. This is not a conversation in any human sense. It is a correspondence across generations, a kind of communication that no individual human will experience from beginning to end, but that a civilization could sustain across centuries if it chose to. The speed of light does not make contact impossible. It makes it slow. It makes it intergenerational. It makes it a project not for individuals but for institutions, not for lifetimes, but for centuries. It asks something of us that is genuinely difficult: the capacity to begin something we will not finish, to contribute to a project whose results we will not see, to care about outcomes that will materialize long after every person alive today is gone. That is not a technological problem. It is a philosophical one, and the universe has been posing it silently at the speed of light for as long as there have been eyes on this planet capable of looking up. The stars are not silent because they have nothing to say. They are silent because the message is still in transit. Every photon crossing the void between here and the nearest star is a physical object, carrying energy, carrying information, obeying the same laws of electromagnetism that Maxwell wrote down in the 1860s. It left its source. It is traveling. It will arrive. The universe does not lose messages. It only delays them. 299,792,458 meters per second. That is not a ceiling. That is the speed of everything we will ever know.